you for inviting me to talk at this wonderful, really special conference. I have to admit that the CGM is less of my expertise. I'm coming from the ISM, but I thought that this might be a good place to try and kind of connect the two and see where there are nice analogies, because from talking to people, I see that we think of the same stuff, just different densities and temperatures. And so I thought it might be useful. And so I'll mostly talk about the multi-phase and turbulent ISM, and to the end, I hope that maybe together we can think of analogies with the CGM. And so let me just start. So in this conference, we usually we talk about the CGM. So this is a cartoon from a recent review paper. But in this talk, I'll really zoom in onto the ISM, the disk part of a galaxy. And here is a nice overview of what's going on, or how do we see the ISM. So the ISM is also highly multi-phased. While the mean density is usually about 1 particle per cc, which is much higher, of course, than the CGM. Most of the gas is found in one of these two phases, what we call the CNM and WNM, the cold and warm neutral medium. And the CNM is usually about 100 or below Kelvin, and the WNM is about 10 to the 4 Kelvin. And of course, there's also hot ionized gas or warm ionized gas also. And this is powered by starlight ionization and by supernova explosions, depending on the temperature we're talking about. So warm is also about 10 to the 4 Kelvin, and hot ionized gas may reach 10 to the 6 or above. Most of the gas, but as I said, is contained in these neutral phases. So H1, the WNM and CNM. The CNM clouds, which are colder and they are also denser, that's where conversion from atomic to molecular phase is happening. So that's where we also see these magnificent star-forming clouds, as this one, the pillar of creation, seen by the HST. And of course, we're in the ISM community, we're interested a lot about the star formation, because star formation also leads to planet formation, this leads to human formation, and this my newly formed human. So in this talk, I will not be talking about the hot ionized phase, nor about the molecular clouds, definitely not about human formation, but more about the warm and cold neutral medium. So I'll be focusing about, when I say multi-phase now, I'll be meaning the multi-phase H1 gas at low temperatures, so at 10 to the 4 and 100 Kelvin. And what I want to focus in this talk is asking a few questions. Is first, how do we know it is multi-phased? Then why is it multi-phased? How these multi-phase structures depend on properties of the galaxy or the local environment, how the phase transition happens, and then they try to find analogies with the CGM. And really in this talk, I'll keep it very idealized, very much simplistic, to try to lay down the basic ideas rather than, bring all the complexities, which are of course there. So don't blame me if things sound too simplistic, but we can discuss this, of course, the complicated parts as well. So how do we know it's multi-phase? There are various ways to observe the ISM, but I think most direct way that suggests that the ISM is multi-phase is from 21 centimeter lines seen in absorption and emission that trace the H1 in the galaxy, as well as in other galaxies. So here's an example. Here what we see is an emission map produced from 21 centimeters using RSCBO, RIP. And these points that you see here are background radio sources, which enable observations of the spectroscopy, absorption spectroscopy around 21 centimeters. Here also we have overlaid some nearby molecular cloud just to complete the picture. Now, if we go to one of these points here, we have emission spectra and absorption spectra. Now, the emission probes the entire H1, so it's proportional to the column density, while absorption is sensitive to the both the column and the temperature, the absorption coefficient. So when we have them together, then we can disentangle the temperature and the amount of the gas, so the column density of CNM, the cold and warm phase, as well as temperatures in between. And what people find is that indeed the temperatures are as low as 100 or below 50 Kelvin or even lower, that's the CNM, and warm gas as well as temperatures in between that we'll see are physically thought to be thermally unstable, and these are roughly the amount in gas mass. So this is the state of the art in terms of observations. Now, why do we expect a multi-phase? And this would be, I think, important if we want to try and compare with the CGM. So here's a very simplistic way to see it, and I think it's different. As we'll see, it's very different from the CGM. But what we have in the ISM, and this is a classical problem that has been discussed since 1968 by Field and Zildovich and Pilkner. These papers here, very interesting, by the way. So basically, the idea is just you consider what are the heating and cooling processes that are effective in the ISM. And heating is usually, at least in our galaxies, dominated by a far UV radiation below 13.6 eV. So it's non-ionizing radiation. That's why we talk about the neutral medium, right? Not the ionized medium. So below 13.6 eV, the UV radiation is not coupled to the gas, right? Because it's not ionizing. So what does it do? How does it heat? Instead, it ionizes dust. So it ionizes electrons from dust, which then thermalize and heat the gas. So it's through the dust that the UV radiation from stars hit the gas. And then there's also ionization by penetrating X-rays and cosmic rays, which are usually not as important, but as we'll see, it might be important at higher redshifts or low metallicity galaxies where there's no dust or less dust. As well as other heating mechanisms, which we'll discuss later, but mainly photoelectric heating from UV. And now for cooling, at these temperatures, so usually we look at you're used to looking at the cooling function at higher temperature, like above 10 to the 4, we have all these ups and downs from H and helium cooling, as well as metals, of course. But here it's mainly Lyman alpha at temperatures of about 10 to the 4, and below it's fine structure transitions of metals, mainly C plus and O1. So it's a spin flip of these neutral oxygen and singly ionized carbon, which is, by the way, singly ionized because the ionization threshold is below 13.6. These dominate the cooling. And basically, the idea, of course, is that the cooling is proportional to n squared, whereas heating is proportional to n, which means that if you equate the two now, cooling equals heating, the temperatures you get depend on the density. If the density is low, then you get the heating rate is higher compared to the cooling rate, and then you get a high temperature. But if as you increase the density, you increase the cooling more relative to heating, and then the heating equals cooling point moves to lower temperatures. So, and this is how you get a steady state thermal equilibrium, thermal steady state as a function of density curve, Dn curve, for the ISM at these temperatures. And this sudden fall of this curve is very important. It is because the cooling function saturates here. Because the cooling function saturates here, that's why we get a sudden fall here in the Tn curve. And this, as we'll see, is very important. This is what gives you the possibility for a multi-phase ISM. So this is the temperature versus density for a given, of course, metallicity, UV intensity, all these parameters curve. And now instead of temperature, we can multiply T by N. We get the thermal pressure. This is what I show here as a function of density. Now remember, this temperature versus density fell very rapidly. This means that now when we plot the pressure versus density, we get this kink. Okay, instead of rising monotonically, we get this point where it goes down. This has to do with the temperature versus density falling down rapidly here. And this is because of the shape of the cooling function that is saturated above 100 Kelvin. So in the end, what we get is this pressure versus density curve that looks like this famous S shape. And what does it mean? It means that if the pressure in the ISM is very small, say 10 to the 3 here, then the solution of the steady state thermal cooling equals heating solution is purely warm gas. So the ISM would be purely warm. If the pressure in the ISM is high, then the solution is purely cold phase. However, there's this range of pressures within which you get these, for a given pressure, you get 3 solutions. So it means that even if the pressure is set, so you assume pressure equilibrium between the phases, and you assume thermal equilibrium, meaning heating equals cooling, you can get several solutions to this equation of thermal steady state. So both this and that are steady state solutions at which heating equals cooling. It means that at a given point in space, with a given pressure, the pressure it might be set by some confining phase, like the hot phase, or by the weight of the disk, whatever it be that sets the pressure. Once you have the pressure, if the pressure falls in this range, at the given pressure, you can get either warm and cold gas. And what naturally happens is that the warm gas segregates and forms small clumps of cold gas within it. And this is very similar to the situation of water droplets that form in water vapor as we reach the boiling point, at which both liquid and gas water, we have both phases at the same temperature at this boiling point. And in fact, this is also discussed by Zeldovich in his paper. So this is a very special situation. It's a steady state situation. And it so happens that independent observations using UV lines of atomic carbon by Jenkins and Tripp show that indeed in the Milky Way disk, the thermal pressure is indeed within this within what is expected theoretically to be multi-phase. So theoretically, we expect this multi-phase at some range of pressures, and observationally, we do see a multi-phase from 21 centimeters, and also the pressure is in agreement with theory from what we accept, where we expect a multi-phase. Now, this is very nice, and a natural question that we may ask here is it a wonderful coincidence that the Milky Way pressure is here? And it might be not a coincidence. So this has to be with the idea of self-regulation of star formation. I'll just go through it very quickly because I want to touch another topic. And the idea is the curve we saw before, the PN curve that we saw, this is for a given condition. So this is for a given metallicity and UV intensity. So this is for typical UV intensity as in our solar neighborhood. Now, what happens if the UV intensity is higher? It means you have a higher heating rate and you have to compensate by higher cooling. So you have to move the curve to higher densities. So this is the curve for UV intensity of 10. Now, what does it tell us? It means, let's say you started with a disk that has a pressure 10 to the 5 here, higher pressure. What would happen is that you look at this curve, you see that the solution is pure CNM. You don't have a multi-phase. So what does it mean? If now you have all the ISM is now cold, it means that you get a very high star formation. Your new curve, your new equilibrium curve will not be the UV equals 1, but it will be this UV equals 10 because UV increases now because of the higher star formation. Until when? Until you get this multi-phase solution. Another way to see it let's say you had an ISM like in our galaxy, so you're placed here and the UV like in our galaxy, and so far for some reason you increase the star formation by a large factor, say a factor of 10. Your new equilibrium curve is now the magenta curve, and you look at the magenta curve, the pressure didn't change. You look at the magenta curve, you see that the solution now is pure WNM, pure warm gas. Now stars do not form in warm gas and diffuse in warm gas, so you stop forming stars until you recover the original curve you had before and the multi-phase ISM. So this is basically the idea of regulation star formation by the multi-phase ISM, which tells you that this is should not be a coincidence that our ISM is multi-phase, but instead it's just the way the interstellar medium naturally tends to regulate itself until it is multi-phase. Otherwise, it has too much star formation or too little star formation. But when it is multi-phase, it has the ability to decide how much gas to put in the cold versus warm phase in order to get it just right. So this is basically discussed in papers by Paravano and Eve Ostreicher, and later papers also there. Finally, okay, not finally, I still want to talk also about the conversion, but before I just want to also mention the dependence on metallicity, which I think is very interesting because when you go to CGM, you typically change the metallicity, and also as you go to higher redshifts or to different kinds of galaxies like dwarf galaxies, you go to different, namely lower metallicities. So, and basically you might expect a very strong effect of metallicity. And why is that? Because both cooling and heating depend on metallicity. Cooling, obviously, because you have the C+ and O1 lines, but heating also because, as we saw, UV is coupled to the dust. So as you decrease metallicity, you also decrease heating. So these curves show you from a paper from 2019, the pressure versus density, but now for different metallicities. Here, Z is relative to solar. So the black line is like the Milky Way. Now, what happens if you decrease the metallicity a little bit, like say by a factor of 10? First, the curve changes, but not a lot. So it remains in the same region. And why is that? Because as you decrease the metallicity, you both decrease the cooling, but you also decrease the heating because there's less coupling between the UV and the dust. So you decrease both heating and cooling rates, so effectively you didn't change anything. Of course, it's not as simple, that's why the shape changes, but you remain in the same region. That's going from 1 to 0.1. If you continue to decrease the metallicity further, then the metallicity is already so low that you're no longer dominated by this heating process, photoelectric heating. Instead, you start to be dominated by other processes that are independent of metallicities, like the cosmic ray ionization heating. At this point, as you decrease the metallicity, the heating rate is independent of metallicity, so it doesn't change. But the cooling rate decreases, of course, proportionally to metallicity. So what happens as you decrease the metallicity, you have to compensate and go to higher, you decrease cooling, so you have to compensate by going to higher and higher densities. So that's what we see from going from the blue to red and to the yellow curve. As we decrease the metallicity by factors of 10, we also increase the density and the pressure by a similar factor. What it means is that if you have a low metallicity system in this range, you'd have to have a higher pressure in the ISM or a higher density in order to allow the formation of the cold phase. Finally, interesting thing that we find that at very low metallicities, almost zero, maybe first galaxies, the metallicity is already so low that other cooling processes, namely H2 cooling, molecular hydrogen that are independent of metallicity, dominate over the metals, over C+. At this point, the different shape of the molecular hydrogen cooling function does not enable a multi-phase ISM. It does not saturate. It always continues to increase the H2 cooling function, which means that you do not get a multi-phase ISM whatsoever. So at this metallicities, you just get a monotonic pressure density curve. And that's it from the very simplistic point of view of one zone models of cooling heating. Before I finish, I also wanted to discuss just in one or two slides the conversion from from warm to cold, how this happens, so a little bit about the dynamics. I think it's very interesting to compare also with the CGM. So this is from already a little bit old paper by Edwin and Abel from 2005, where they collide two streams, 5 minutes, okay, where they collide two streams of warm gas, so the W and M, and then they watch what happens. And what happens is that you get first you have a shock, so you have an increase in the temperature and the density and the pressure. So if you start with the W and M here, you go up there along this cyan line, you quickly cool down back to 10 to the 4 Kelvin. And now it depends. If these streams continue to be there for a long enough time, how much time? The cooling time. If the streams continue to be supplied over a cooling time, so you continue to be at this high pressure state for a long enough time, for the cooling time, and until you start cooling, and then you cool back to the CNM. So that's a conversion. On the other hand, if you stop these streams after short enough time, before cooling kicks in, then you relax back to the WNM. So basically, the criteria is that the time scale over which the stream should be coherent should be of order of or larger than the cooling time, and then you get a conversion from warm to cold. That's what they find. And then when they zoom in their simulations, they also find an interesting thing, that a size scale of these cold cloudlets that form is of order of T cool over CS, which is also highly discussed in your literature, which we'll see in a moment. Each clump in their picture is thermal, but the relative velocities between clumps is of order of the velocities of the W and M, so the sound speed of the W and M, which would be super thermal in respect to the sound speed of the cold gas. And this, I think, is very interesting to compare with the papers by McCord and Gronker, and of course other papers that talk about this process of segregation of warm gas into cold, and what's the size scale is CS over T cool, and then there's discussion if it's T cool of the hot phase of T or T cool of the cold phase. But in any case, in the context of the ISM, I think it's not enough discussed what would be the structure and if it's a mist or a cloud. Whereas it's nice to see that it's very interesting in the CGM. People are interested in that a lot. Oh yeah. Finally, I also wanted to just mention a very new, a relatively new technique that is used now in the recent 2 years in the ISM to observe the interstellar medium structure in 3 dimensions. So recently, with the launch of Gaia and wealth of data from Gaia and parallel access to stars, there's a new technique called 3D dust mapping, which allows the observations of the local ISM around us, the structure in 3 dimensions. And this is for what you see here is actual 3-dimensional data of local clouds in the solar vicinity. And we also combine it with VR, so virtual reality and augmented reality. And now this is placed on the table, and you can move around and look this. And this is so this is a nice new cool stuff that we're playing around with. So to summarize this tutorial, and I hope many will join to the breakout room to discuss these items. So what is different? So the right panel talks about the CGM, and here really I placed question marks because you're the experts. And here the left panel is ISM. So for the ISM, for example, the multi-phase may be viewed as some steady state configuration where we have heating and cooling balance at the same location and pressure balance. And it's just the way the cooling function looks like, and that the fact that you always have a steady and very effective heating source in the ISM. Is it like this in the CGM? From what I think, it's not, because I feel that it's quite elusive what's the heating source, and if it's steady or not, probably not. But you tell me. And then for phase transition, I hear similar ideas, qualitatively, of course, for the CGM and ISM, where you have the T-cool of a T-stream larger than 1. In the CGM, people talk about T-cool versus TFF larger than 10, and I wonder if it's maybe looked as a similar analogy, that you have to have these colliding streams long enough before the clouds disperse because of these gravity waves, but here it's the streams or turbulence, whatever. And the size scales, as I discussed before. And some open questions that I'm interested in is, what's the abundance of the cold versus hot phase in the ISM, and what's the transition mechanism? And then what's the structure? Is there a typical size of all the CS over T cool, or is it a continuous distribution as often suggested by turbulence models? And finally, should we expect also real cold gas? So not 10 to the 4, but what we call cold, like 100 or below clouds and star formation in the CGM. And that's it, I guess. Thank you.
Thank you so much.